So next up, we have an amazing speaker as well, the CEO of Lepton AI, Dr. Yangqing Jia. He has a great history and past. If you remember the deep learning framework camp, he was the mastermind behind that out of Berkeley. He's run AI at Facebook, AI and analytics at Alibaba, and was also part of the Google Brain team. So without further ado, let's welcome Dr. Yangqing Jia to give his talk.
Thanks so much. Thanks. Just looking for my clicker here. It's a great honor to be here, and as a Berkeley grad student, a little bit nervous to be standing in front of the Stanford podium, but go Bears. I grew up back in China, so I usually want to basically start with an analogy of how AI can be not really like this super mysterious thing. Back in my kids' days, I actually had a project. Well, my parents work in high school, so I actually got the privilege to see a Chinese typewriter. If you think about it, a typical typewriter has 26 keys, and we already trained our fingers to basically type those keys as fast as possible, right? China has 3,000 common characters to start with, and the typewriter looks something like this. If you go through San Francisco Airport, you might have seen it before. It's a big board of different kind of characters, and then there's basically just like this big handle that moves around this board, picks the characters, and then basically pushes it, prints it, like brings up this like little thing, and then puts a keystroke on the scroll on the top. Now, one of the biggest challenge is how do we actually algorithmically trying to optimize the speed to type in on that typewriter. We already know QWERTY and all those. If you're a geek, you know there's other keyboard layout like Dvorak and things like that. Basically, the idea is how do we actually put the optimal layout so that we actually, like type things as fast as possible. Now, it turns out that we have actually solved that problem by an earlier version of AI, right? When you look at an earlier version of these kind of type-in layouts, then the idea is simple. First of all, the most frequent ones should be in the center or in some blocks that are like always easy to access, like things like here, which is simple. And then we go a little bit deeper by looking at the statistics of co-occurring words. In China, there are words like, say, 中国, which means China, and then like 中华, which means the Chinese ethnic group, and things like that. So we go through all those books and basically try to find connections. We put closer words that are co-occurring always, together closer on that board. In the computer science world, we call it bigram, right? If you have been through like NLP classes and things like that, basically co-occurring words have a higher probability of occurring together in a text. So basically, like when you want to basically type things, you don't really want to move that handle really far away when you're typing. You want to basically type things as close as possible. And that, I would tend to think about it as the early version of AI and ChatGPT in some way. ChatGPT, as Ilya would probably describe, it's basically really sophisticated and smart algorithms for us to find out what next word is, and that's basically a version of it. But so much about it. I kind of started doing AI at Berkeley and then very quickly went into the system world, and the idea that today we are actually doing a startup is mainly because we saw the huge need for computation and a better infrastructure to use AI as like a more efficient tool for everyone, not only just AI scientists, but also people who are actually having a lot of real-world applications in their hands. Our co-founders, just a little bit of bullshitting, created some of the most popular libraries, such as Caffe, PyTorch, and also etcd, which you might not have heard about it. It's the database that runs Kubernetes, basically all the cloud-native kind of stuff. And one thing I wanted to basically share is that we have a strong belief that AI is probably going to be the third biggest pillar in the IT or computing infrastructure. We've seen multiple rounds of different kind of computer infrastructure designs and things like that, and we think that AI is different enough to be the third pillar. The reason we think about it is if we think about the ways that people are, well, actually, before that, let me just use some statistics to show that, right? 10 years ago, when we were basically doing Caffe, which is an open source library for AI, then the GitHub star went really fast. The red curve is basically how people react on GitHub of the Caffe project. We thought it was probably the fastest. In 2017, PyTorch came out, and there was actually a much faster gain of stars on GitHub. This year, there's a project called AutoGPT. Its performance, its quality is debated, but people have a really, really, really strong interest in using it. And as a result, what we are observing is that within something like a month, it already gained something like 140,000 stars, which shows that like those kind of AI applications has been really, really popular. Now, AutoGPT runs on top of GPT, and we know that GPT has been hogging down quite a lot of computation resources and things like that. And when we look at those kind of computation patterns, they're quite different from the existing either big data computations or web computations. And allow me to basically quote Professor Richard Sutton, one of the pioneers in reinforcement learning, which is a topic for our last speaker. He basically says, the biggest lesson that we learned over the last 70 years of AI is that general approaches, and today most of those are neural networks, general approaches that leverage computation are ultimately the most effective approaches. We find a general algorithm that's like generalized enough to encode a lot of knowledge in that model, and then we basically feed it with a huge amount of data and have very powerful GPUs and things like that to chew it multiple times and then produce a really good model. The computation patterns allow me to dive a little bit more into the technical details, have a very interesting characteristics. Now, starting from the 1970s, one of the really important part in IT infrastructure is about databases, right? There's Oracle databases, there's IBM DB2 and things like that. Databases are hugely distributed systems, and today we see cloud databases such as BigQuery and things like that. It orchestrates a huge amount of machines to basically do sophisticated computations like summarizing terabytes or petabytes of data and things like that. Surprisingly, the abstraction is actually really easy, right? We've probably heard about the term SQL. If you basically want to figure out what is, back in Alibaba days, if you want to figure out what are the average number of people's spendings on Taobao or Amazon, basically, per month, you basically say, well, select average of spending over like group by month, and then you just like to average and things like that. Very simple syntax allowing you to immediately orchestrate a huge amount of compute. So for users, it's really easy, but infrastructure, and luckily over so many years, have been kind of stabilized so that we can basically utilize those complex infrastructure very easy. The other trend starting from the 1990s is basically web services. The idea is that we're having really little services that really optimizes I/O, strings, web pages, and things like that, and there's not too much compute. Each single web service is kind of small. One computer, one really big computers these days, can host maybe hundreds and thousands of such compute units, and we call it microservices. Now, when you think about parallelizations, these kind of things are a bit easier because you just replicate that little service, and then you basically, like, depending on the traffic, you copy it multiple times across different machines and things like that. So it's kind of, I'm not saying it's the easiest, but it's kind of easy to use. And infrastructure-wise, orchestrating utilization is always a big problem, but it's kind of easy, a little bit easier than databases. Now, if you think about AI compute, things are kind of trickier because you probably heard about GPUs, and then you need to shovel 8 GPUs in one box, and then GPU clusters and things like that. It's relatively hard to manage. And when you think about designing a model that can basically run across different machines and things like that, it's kind of hard as well. So it's pretty hard to use, pretty hard for infrastructure. It's kind of similar. One big similarity is the scientific computation world. Basically, like people who are basically doing massive physics simulations, or for better or worse, like nuclear simulations and things like that. Really complex computation patterns and really hard infrastructure, which is why we think AI should really be considered slightly different from the existing infrastructure that we are having today, either databases or web compute. But, when we think about these kind of complexities, we kind of feel that for really big systems, there are those kind of solutions. And we think when we look at the landscape today, we kind of feel that there are already really good solutions out there. There is open source llama models that Facebook trained from thousands of GPUs, and now they're out. And general purpose models seems to be working pretty well, like GPT and things like that. And it starts having us thinking about, is size the only thing that matters, right? Do we need a huge amount of databases or data to just train a model? Or in our specific domains, we can actually use a small amount of data to actually train a more specialized model. The interesting is, if you think about it, ChatGPT today is hugely luxurious, right? We're literally talking to someone, the equivalent of someone who got a PhD degree in Stanford, Berkeley, Harvard, and MIT, and can talk Shakespeare to you and knows all kinds of music scores and things like that. Well, of course, now you only need to pay $20 to access it, but you know for a fact that under the hood, the price is probably not manageable. And sometimes in your specific domain, even that powerful triple PhD isn't able to solve your problem. And I'll give you one simple example that we kind of tried out as a cute experiment. We've all heard about, like earning calls and things like that, and we're like, well, what if we could train a small model that sounds and analyzes questions like a CFO would do in earning calls? Now, we basically crawled the data from all those earning calls, transcripts, and then we trained a model. We fed the model with Apple's last Q2 earning, and we basically asked it questions like, can you talk about a little bit about how AI would impact Apple and how do you think about it? Now, a general purpose model like ChatGPT is very honorable. It is really not trained and is actually aligned to really optimize for things like generality. And then basically it says, I don't know. Now, for the specialized model, it basically says, well, sure, thanks for the question. It already starts sounding like a CTO, right? It's like, as you know, we've been using AI and things like that, and it's very, very CTO-like. This is only, like a couple of megabytes of data, and it's already pretty good. How to train it? We basically get all those transcripts as question-answer pairs. This is a little JSON file. We don't need to read the details. Basically, we organize the training data into questions, answers, and things like that. If you're working on customer support, those kind of data are already probably sitting on your disk already. Now, we built a system that allows you to basically upload that data into a training system. The training algorithms today are surprisingly standardized. We kind of basically standardize, how you can actually distribute training on different GPUs and things like that, and make it as easy as possible for you to just crunch a model out of it. That training takes, for smaller data, a couple minutes, and longer data, a couple hours, and then eventually you just get a model. Sorry for the characters, a little bit small. On the platform, it basically exposes itself as a model. And then on top of that, a model can basically say deploy. And we can use standard LLM deployment mechanisms to basically ship it as, like a chatbot. And then you can immediately start experiment with it and things like that. And we actually worked with Inomatic quite a bit about, like industry applications and things like that. We think there's quite a lot of opportunity, although, we are also learning quite a lot about how specific verticals would affect the training algorithms and efficiency and things like that. Now, basically, the other thing is, you might think about, well, LLM is great. Can I own it? How expensive is it? Surprisingly, it's actually not as expensive as you think. Now, let me do a bit of a mathematical accountant kind of calculation. So in addition, let's throw out the questions like privacy and security and things like that, which is hugely, hugely favoring your own models, right? Let's throw out those and talk about the cost effect. There's a common model called Llama 7B, which is actually really good for specialized models. And that can be run on smaller scale GPUs such as A10, which has 24 gigabytes of memory and things like that. On AWS, we just use standard pricing. A10 costs about something like $0.6 per hour. It can actually produce as many as 2,500 tokens per second. And in comparison, people talk about 120 tokens per second, right? So if you think about it, it's actually able to basically crunch out something like 9 million tokens per hour, which is usually good enough for a lot of applications. And if you think about the total annual cost of ownership, it's $5,000, which is kind of fine. So what I want to basically say is, it's actually probably going to be really efficient if we can have a specialized small model and actually ship it with your own infrastructure and things like that. Now, we, of course, help you to basically go from the machine learning algorithm side to a lot of other surrounding capabilities and stuff like that. This is from a very famous Google's paper called Machine Learning, the High Interest Credit Card of Technical Debt. In addition to that algorithm, there's a lot of things like data orchestrations, model quality, serving infrastructure and things like that. And we basically take care of that for you. As a high-level idea, then basically, like if you are using, the OpenSSA kind of architecture, and then we can basically, under the hood, we can use the Lepton platform for you to take care of a lot of the infrastructural pieces, such as, hardware supply chains, like cloud infrastructure, data infrastructure, things like that, and help you to focus on basically doing serving, tuning, DevOps, and things like that, and then ship those kind of things into either a model API that your colleagues and friends can basically integrate into their applications, or build a vertical SaaS solution. To give you a little bit of idea about what kind of things we could be doing, then imagine, if we are a data scientist and we're like, well, all those kind of bells and whistles about AI, we probably want to throw it out. And I just want to run some Python code, say model equals to some awesome model, and I want to call into it. This is exactly what we do without touching too much details and making it sound like a sales call. You can basically just load a model, a Hugging Face model, by providing the string, and then it just gives you out the results. There's a lot of specialized models out there, and I'll use a Chinese language model as an example. There's Japanese models and Korean models, because for different languages, actually, specialized models work much better than general models, right? You can just pull it up, and then you just start using it. This is basically saying I love walking the dog, and things like that. Okay, so there's also APIs and things like that, but this sounds too much like a sales call, so I'll just skip that. With APIs, it's a little bit easier for you to just get started and then start integrating and trying out if those models are good enough. The next question is, now, if we already solve all those kind of problems of large language models or natural language processing and things like that, does AI only involve language models? The reason I want to say this is mainly because there is such a big popularity or such a big mind share of language models. It seems as if we just need to call GPT or Llama and solve all the problems. My argument is probably not. Even today, we're seeing quite a lot of different kind of use cases using AI to generate images, using AI to do conversation bots to help you write code. And this is basically writing SQL code, doing conversations, which is the classical NLP kind of problem, and also other kind of applications like recognizing voices, using AI to generate cute images to assist design and things like that. Quite a lot of uses are beyond natural language processing. And if you look at statistics, there's this really famous platform called Hugging Face, and the number of models on Hugging Face surged like crazy. Last year, there was about 65,000 models last August, and last month when I checked, that number surged to 334,000 different models. Lots of the models are, understandably, half of the model are actually natural language processing, but there is also other models such as computer vision, speech, and things like that. In language models, there is not only just LLM type models, there's also sentiment analysis and all those conventional models that actually work at a much higher efficiency and also higher quality. So the idea is, how do we actually utilize that big group of models and find the one that fits you most? On the demand side, of course, we see more and more applications, according to Gartner, more and more applications that are starting to use AI, and plausibly, a simple conversation model would probably not fit your purpose. All the more reason for you to basically use a platform and ease the way of choosing models and using models as a data scientist, and then focusing your time on actually, figuring out what kind of model works best for your application. As an example, I'll basically share one experience that we had back in the Alibaba days serving industrial customers. And we feel really proud and at the same time humbled, because those actually teach us quite a lot. The application involves managing airports. Now, if you've flown in and out of New York in a stormy day, you know that when your plane hits the ground, your immediate thought is, how do I get off as fast as possible, right? But your plane circles around JFK because there's congestions and things like that. Trust me, you hate it. The airport hates it too, and the airlines hate it too, because that's basically dead time that planes stay on the ground, right? So we want to optimize it. Now, there are poor ATC gentlemen and ladies who are on the tower trying to figure out through all these kind of crazy chaos, which is kind of hard. We worked together with my home airport back in Hangzhou, China, and we were like, how do we actually digitize it? We could use computer vision algorithms to basically find out where the planes are and what their trajectories are, classical object detection and tracking kind of problem. right? We can then basically put all those things into a database, conventional database problems, and then using data analytics, big data to basically sort out and find what kind of hotspot there are. People make mistakes, and ATC personnel sometimes route planes in their common habit, which unavoidably sometimes creates congestion point. And with an algorithm, you're actually able to look into that and actually find those kind of hotspots. And then basically, we can be a very helpful agent to allow the ATC gentlemen and ladies to basically route the planes in a much more efficient fashion. This is the bullshit story. When I fly back to my home airport, congestion is still pretty bad. So we kind of feel that AI doesn't really solve all the problems, but we at least found a way to help us to understand this kind of real world really well and make sure that we can then help data scientists and all those in-domain experts to analyze their problems in a much more specific, domain-specific and expert-led kind of way. Which is why I think SSM is a pretty good idea about a pretty good principle to think about and approach those problems. I want to basically finish by talking a little bit philosophically and think about how should enterprises do, what should enterprises do to embrace AI? Are we going to be doing fundamental research, or should we actually focus more on the application side? And for this, I'll probably cite the interest in I think what people call Pascal's quadrant, basically. And if you think about things from two angles, one is, are we actually going to be on a quest to do more fundamental understanding of the nature of science? And the other angle being, how much do we care about use, actual use? Then you can put things into 4 quadrants. Well, if it doesn't really help us understand the world and doesn't really help us to make applications, we don't care about it. There's the Niels Bohr kind of quadrant, which is basically saying, trying to understand how quantum mechanics work. It doesn't really have too much uses, but it helps us to fundamentally understand the world. There is the Louis Pasteur quadrant, which is it has a high level of understanding about how biology works, and it has a high level of usage potential, which is how do we actually do pasteurization. Pasteurization is actually named after Pasteur, right? I kind of feel that today AI is in this, what we call the Thomas Edison kind of quadrant. Large language models and the fundamental understanding about how we design algorithms is good enough for us to unlock quite a lot of applications, but we're still quite far from actually closing the gap between an algorithm being out there and being used in a lot of real-world applications. Now, if you think about chatbots and things like that, those are easy and those are fast, right? But if you think about industrial applications, there's so much domain knowledge that the infiltration, or basically the trickle-down effect, is going to be much slower than what we would expect in using Stable Diffusion to create some cute images and things like that. But we see that as one of the biggest opportunities, and that's why we are pretty excited about basically building a platform and helping people to do that. With that, I'll probably finish my bullshitting or talking and things like that, and I hope down the road we'll be able to help with a scalable platform and our infrastructure knowledge to help you build more awesome domain-specific applications and use AI to change the world in some sense. Thank you so much.
Slide that mentioned SSM.
Right.
Can you explain what that is?
Yeah, I thought some speakers actually mentioned that in earlier today, which is why I directly referred to that. So there's the notion of large language models, which is hugely general, and basically it answers you the question of the world in some way. But when you look at specific domains, such as industrial applications and all those other things, then it's probably not as accurate. So I think the idea of building specialized small model is to help language models to, one, understand a specific field as much as possible, and the other thing is basically to make sure that we are actually shaving off the unnecessary Shakespeare's and musics and all those things from the large language model and make it actually cost-effective, maximizing the performance and minimizing the cost. I think that would probably be the long way to go. And in fact, actually yesterday, Clem, the founder of Hugging Face, actually said that in the future, people will probably deploy more specific domain-specific models instead of continuing leveraging in a very luxurious way general large language models to solve every single problem. So I think SSM is actually the way to go, and that will be creating a more efficient and high quality application for sure. Specialized small modules, yeah.
Thank you, Dr. Jia, once again. Appreciate you being here.
Awesome. Thanks so much.